Now that we have a periodic table to organize all of our elements, let's see how those elements vary as we move around on the periodic table. Our learning goals are going to be simply to understand the trends and physical properties of elements as we move across the periodic table. This is going to involve some understanding of electron shielding of the atomic nucleus. Okay, now what I want you to begin to gain an intuitive feel about is that core electrons can effectively shield the charge of the nucleus. So let's consider a couple of different cases. Let's imagine that we have a bare nucleus somewhere in the universe, and there's an electron that happens to get close enough to see that nucleus and feels a very strong attraction, because according to that electron, all of the charge is available for that electrostatic Coulombic force. On the other hand, let's suppose that nucleus happened to have core electrons around it. Now what does that electron see? Okay, the core of electrons around the nucleus begin to counteract the charge of the nucleus. And in fact, they have a repulsive force with that electron that's coming in from outside. So they're counteracting the attraction of the nucleus, which means that the effective charge of the nucleus looks something less than just its full charge of plus n. So that electron now that's coming from outside is going to feel a weaker attraction to that nucleus. All right, this is at the heart of what we're trying to learn about here in the periodic table. What we want to know is, how does that shielding affect the properties that we eventually will see and observe in these atoms? Now, let's start by considering atomic size. What factors would influence the size of an electron cloud around an atom? Okay, the electrons are attracted to the nucleus of the atom, so they're all going to be somewhere around that nucleus. Their size around the nucleus is going to be dependent upon the size of the electron orbitals. That is, in larger energy shells, we're going to have larger orbitals, but it's also going to be affected by the strength of the nuclear charge. So as the nuclear charge increases, we should see a change in the attractive force between the nucleus and those electrons. So we can characterize these two things. Orbital size is going to increase as we move to higher and higher electron energy levels. Okay, we're getting farther from the nucleus, so the orbital size has to increase. But as we move from left to right across the periodic table, we know that each new atom has one more proton than the previous one. So the nuclear charge is increasing as a whole as we move across. The stronger charge as we move across means the electrons are pulled in closer. So let's see what those trends mean for the first 20 or so elements. Okay, when we draw their size, and based on different kinds of criteria that one might use to define atomic size, we would see the following trends. Now, it's easy to see from the various shapes here that atomic size is increasing as we move from right to left, and also as we move from the top to the bottom. So the very biggest atoms, the biggest one shown here is sodium, Na, and the smallest is helium. Okay, and that's going to be a general trend that we'll see in the periodic table. Right, what we don't understand, and this is all due to orbital size increasing as we move down, that tells us why each row is bigger than the previous row. What we don't understand, though, is why magnesium might be larger than sulfur. Okay, and this is going to have to do with the effective nuclear charge. Let's draw a board diagram for each of these. Now, I've drawn magnesium on the left, which has a plus 12 on it, charge on its nucleus, and sulfur on the right with plus 16 charge on the nucleus. Both of these have the same number of core electrons. They both have 10 core electrons, which corresponds to the number of electrons you find in neon. Okay, those electrons can shield reasonably effectively the nucleus, but valence electrons don't do such a good job of shielding the nucleus. So what that means is that the nuclei on the outermost part, the valence shell of these two atoms, is going to be shielded to the same extent by that group of core electrons. So the only thing that's different between these atoms now, besides having a few more valence electrons in sulfur, is the charge of the nucleus. And the sulfur charge is much greater than the magnesium charge. So that means the electrons in sulfur are pulled even more strongly toward the nucleus, because they're shielded by the same amount as those in magnesium, but there's a stronger nuclear charge. So this is what accounts for sulfur being smaller than magnesium in atomic size. Now, we also want to look in terms of physical properties at electron loss and capture. Atoms can lose electrons or capture electrons from other sources. Okay, this is a very dynamic process for atoms. They're governed by the same factors that determine the atomic size. So if there is a strong nucleus electron attraction, then we're going to have a smaller atom, but we're also going to need more energy to remove that electron. It's also true that more energy will be released when the electron is added. That is another electron from outside that atom. Okay, we can think of this analogy as being like the depth of a hole. So going back to that analogy we drew before, if these are three holes and they represent different amounts of nuclear charge, okay, we may have a smaller atom because we have a high nuclear charge, a deeper hole, and it requires a higher escape energy, so that electron is held more tightly by the nucleus. That represents the strong attraction. If there's a large atomic size, that means we have a smaller nuclear charge, a more shallow hole, a low escape energy, and a weaker attraction. All right, so this is how these two get balanced. Now, in terms of the periodic trends, what we might see is that the ionization energy, which is the energy cost for losing an electron from the valence shell, pulling an electron out of an atom, okay, that is going to be affected, as is the electron affinity, which is the opposite, the energy that is released when an electron is captured by an atom. Okay, electron affinity, strictly speaking, is less than 0. We're going to focus on magnitude here, as we do in most chemistry books, and only consider its magnitude, even though you should be aware that electron affinity is in fact a negative energy. All right, both of these vary in the same way. In other words, smaller atoms, the ones toward the top and toward the right of the periodic table, are going to have a larger ionization energy, and they're also going to show a greater electron affinity, a greater magnitude of electron affinity, because the valence shell is attracted to the nucleus more strongly in those cases. You should note that these are the opposite of the atomic size trends. So smaller atoms mean large ionization energy and large electron affinity. Large atoms mean small ionization energy and small electron affinity.